Hi guys, welcome to day 2 of probability. So what we're going to do today, we're going to look at some stuff that has to do with disjoint and overlapping events. And really this becomes a big deal when we have an or going on in our problem. And so if two events are disjoint, that means, or mutually exclusive, in other words, you might see for the same thing, that just means they can't both happen at the same time. So for example, if I said pulling a 7 or pulling a 2 out of a deck of cards, it's impossible to pull out one card that's both a 7 and a 2 at the same time. Therefore, those events are disjoint, mutually exclusive. To contrast that with the other one, overlapping events can happen at the same time. And so if I said, what's the probability that you pull out a 7 from a deck of cards and a spade from a deck of cards? Well, a card can be a 7 and a spade at the same time, and that means those are overlapping events. They can both happen in the same trial. All right, so does that make sense, kind of the difference between the two? And that's going to be our two big ideas today, disjoint and overlapping events. And we're going to see what happens differently when we have those, especially with an or. And remember from yesterday, our U thing means or the union between these two things. So let's do an example. All right, so what I have going on in this first one is you have a six-sided die. So just like you get with whatever board game, dice is the plural, die is the singular. So if you have a six-sided die, what is the probability of rolling a 2 or 5? And so or, remember, is like our operator word here. And so we need to think, are these disjoint or are these overlapping? Is it possible to roll a single die, we're not talking two, we're talking one die, and roll a 2 and a 5 at the same time? Can't happen, right? You can roll a 2, you can roll a 5, you can't roll both at the same time with a single die. And so let's talk about the probabilities of each of these individually. What's the probability of rolling a 2? Well, if there's 6 sides on this die, there's only going to be one side that's a 2, and so the probability, there's one desirable outcome, that's the 2, out of the 6 possible outcomes, so the probability is 1/6. And if you wanted that as a decimal or percentage, like we said yesterday, that would be fine. The probability of rolling a 5, well, on a die there's only one side that's a 5 out of the 6 total sides, so the probability of rolling a 5 is 1/6. The probability of rolling a 2 or a 5 then, well, if there's a 1/6 chance you roll a 2, there's a 1/6 chance you roll a 5, and they're completely separate from each other, then to figure out the probability of either of them happening, you just add them together. And that's what this formula here is really saying. If the two events are disjoint, don't overlap at all, can't happen at the same time, to find the probability of one or the other, you just add the two probabilities together. And so 1/6 plus another 1/6. Now remember, the way we add fractions is we have to have a common denominator, which we already have here. 6 is on the bottom of both. And 1 plus 1, we add the numerators, keep the denominator exactly the same. So in other words, we've got 2/6. So a 2 out of 6 chance, or we shouldn't leave it like that because remember, we said if you're going to leave it as a fraction, it has to be in simplest form. And so if we want to leave it as a fraction, we'd have to change that to 1/3. So we've got a 1/3 chance of rolling a 2 or a 5 when we roll a die. All right, does that make sense how we got that? Now, the other option, what if the events are overlapping? In other words, what if the events can occur in the same trial? All right, so what we're going to look at here is what is the probability of picking a king or a face card from a standard deck of cards? All right, so this is where if you have the reference sheet I gave you on Google Classroom about a standard deck of cards and how it works, there's some helpful information for this on there, but I'm going to kind of mention it all here. So kings are the ones with the K's on them. Face cards are any of the cards that have a face on them, basically. A king, a queen, or a king. Or sorry, a queen, a king, or a jack. Those are the 3 cards that have faces on them. Now, there's 3 cards that have faces on them, but there's 4 suits, and so there's 3 of each suit, which makes a total of 12 face cards. And so our total face cards are 12. And so let's just find the probability of both of these things first, and then see if we can figure out what we have to do to make this an or. So the probability that you get a king. All right, so in a deck, there are 4 kings out of the 52 cards. So that's 4 out of 52, which I know simplifies to 1/13. Now, in a minute, I'm probably going to leave it like this because it's going to be easier and give us a common denominator. So probability of a king is 4 out of 52, or 1/13. Probability of a face card. Well, we said there's 12 face cards in a deck. And so the probability that we get a face card is 12 out of the 52 cards. Right? Now, if I go to simplify that, 4 goes into both of these. 4 times 3 is 12. 4 times 13 is 52. So there's a 3 out of 13 chance that we get a face card. So what's the probability that we get a king or a face card? Well, kings, there's 4 of them. So we've got 4 out of 52. And we said a minute ago, if it's or, you add them together. And like I said a minute ago, instead of doing the simplified versions, I know that this is 1/13, but I'm going to leave it as 4 over 52, because if I'm going to add fractions, I want to have these like denominators. And I know that we end up with a like denominator here, but we might not with what we have to do in a second. So we've got 4 out of 52 that are kings, 12 out of 52 that are face cards. Now here's the problem. That would make 16 cards that satisfy both these things. However, there's an issue here. Because we counted all the kings, we counted all the face cards, but aren't the kings also face cards at the same time? So that means, since I counted the 4 kings and the 12 face cards, all these kings got counted, all the kings got counted in this group and got counted in this group, which means they all got counted twice. That's a problem. And so if I want to have just the kings counted once, then I have to subtract them all off one time. So let me go through that explanation again, because I feel like this is the hard part of this. So there's 4 kings, 12 face cards. However, of these 12 face cards, 4 are kings. And so we counted the kings in this group and the kings in this group, which means there's 4 cards, the kings of each suit, that got counted twice. We can only count them once, and so I'm going to subtract off that 4 cards that I counted twice, which gives me, in the end, 12 out of 52, or in other words, we saw that a minute ago, 3 out of 13 chance that we get a king or a face card. So that's the probability of a king or a face card. Now let's see if we can generalize the formula for what happens here. It's going to start off looking a lot the same as this, but we have to put one more thing at the end. For overlapping events, the probability of A or B is still the probability of A plus the probability of B. But then at the end, we had to subtract off this part that was in both at the same time. Since there's 4 cards in this case counted in both, I subtracted that off. There's another word we have for when it's both at the same time. Isn't that what and represented that we learned yesterday? So what I'm going to do is I'm going to subtract off anything that is in both, the probability of A and B. Stuff that is both at the same time, because everything that's both A and B at the same time is getting counted in this group, and it can't be counted twice, and so we have to get rid of it once. And so for overlapping events, that's our formula. And really, if you wanted just one formula to know for this, it would be this, because this actually still works in that case. Because if I go back to this, the probability of a 2 is 1/6. The probability of a 5 is 1/6. What's the probability of rolling a 2 and a 5 at the same time? It can't happen, so that means the probability of that part is 0. And so this formula still works, it's just this part is 0 because there isn't any probability of rolling the die and getting a 2 and a 5 at the same time. It's not possible. So that gives us the idea of what happens when we have OR. Now next I want to look at some two-way tables, but let's take a second and enjoy a musical interlude while we switch to our next thing. Alright, so next up, we're going to look at some stuff about two-way tables. And so this is something new to you guys. And they're called two-way tables because we basically have rows of stuff that's showing us information, and then we have columns of stuff that's showing us information. And so putting it together, we have two waves of information put together. And then you notice we have these total columns. Sometimes these are left off and you have to kind of figure them out for yourself. I went ahead and put the total columns on here. And so I want us to think about this particular one. So this is a survey about breakfast habits for students in middle school and students in high school. And so we have 14, basically the 14 here says 14 middle school students skip breakfast. The 12 right here would say 12 high school students eat breakfast. So let's just get the idea of how this works down first, and then we're going to see if we can do some probabilities that go along with that. So first off, looking at this information, let's see if we can figure out how many total people were surveyed here. And so if you look at what we have going on here, we have this total column, and right here we have the total both directions. And it comes out to the same number, 38 plus 52, 36 plus 54. They both equal 90. This is our total number of people surveyed. And so we asked 90 students about their breakfast habits. All right, how many total middle school students were surveyed in this? Well, that means we're only looking at this column, so the total number of middle school students. We had 14 who skip breakfast, 40 who eat breakfast, so that means we asked a total of 54 middle school students. All right, and then total number of breakfast skippers surveyed. So people who skip breakfast are only in this column. So we've got 14 middle school students, 24 high school students, which means we have a total of 38 people we surveyed who skip breakfast. All right, so just making sure we have the idea of how to read this table down there. Now let's see if we can compute some probabilities that go along with the information here. So what is the probability that a student is in middle school? All right, so if they're in middle school, we have to think how many total middle school students do we have? And we're just worried about if they're in middle school. We're not worried about if they eat breakfast, skip breakfast, doesn't matter. Middle school students, we have 54 total out of our total number of students out of 90. And so probability that a student is in middle school is 54 out of 90. Now, when you start to get into bigger numbers like this, you could simplify this fraction. That's just fine to do that. And especially some on your guys' homework are out of like 1,000 and some people. Simplifying fractions with those big numbers is not impossible, but it is a lot of work. And since you can do probability in terms of simplified fractions, decimals, or percentages, let's just change these big numbers into decimals or percentages. So I'm going to do 54 divided by 90 here. And if you do 54 divided by 90, this comes out to 0.6. And so you could just say the probability is 0.6. Or if you move the decimal point 2 places, if you like a percentage, there's a 60% chance that a student picked out of this survey is in middle school. All right, so next up, what is the probability that a student eats breakfast? All right, so breakfast eaters, total number of people who eat breakfast is 52. Some are in middle school, some are in high school, but we're just looking for who eats breakfast. We have 52 out of the 90. And so this would be 52 out of 90. And again, we could simplify that, but instead I'm just going to try to change this to a decimal. And changing this to a decimal, we get, it's not quite as nice on this one, 0.57 repeating. Or about 57 point, we'll say 0.8% if we round up. And so that's the probability that a student eats breakfast. We have 52 breakfast eaters out of the 90 students we surveyed. All right, part C. Remember, we've got a couple operative words, and I know I've been circling them or underlining them or something on the problems up until now. I didn't on this one at first, but remember, this is really an operator. It tells us something we have to do. So what is the probability a student is in high school and skips breakfast? All right, so looking over here, we've got 38 students in high school, all right, or we've got 38 breakfast skippers. We've got 36 students in high school. However, we're looking for the people who do both. And means both have to happen. So how many students are in high school and skip breakfast? That's the 24 right here. Those are high school students who also skip breakfast. And so we've got 24 out of the total of 90 students who are in high school and skip breakfast. And again, I'm going to turn this into a decimal or a percentage to make it a little easier to work with. So this is like 0.26 repeating. Or if you want it as a percentage, it's 26.6 repeating. You could say percent. All right, and then our last one. This is kind of where it starts to have to do with the stuff we learned earlier today. Do you notice our operator on this one? We've got the word or. Now, or means if either of these things happens, it's a desirable outcome. We don't need to have both of these things happening. So what is the probability a student is in high school or eats breakfast? All right, so high school students, we've got 36 that are desirable outcomes because they're in high school. And so that's 36 out of 90 that are desirable outcomes because they're in high school. But if you eat breakfast, that's also a desirable outcome. So eating breakfast, we've got another 52 students. All right. Now, if I just add those two together, you're going to notice something that is not going to work here. So if I add these two together, that means 88 out of the 90 students we're saying either are in high school or eat breakfast. And looking at our stats over there, that doesn't seem to be the case, that almost everyone is in high school or eats breakfast. So we've got a slight issue there. And the issue is we've counted many of these students twice. Do you notice this is all the students who are in high school. This is all the students who eat breakfast. The problem is everybody who is in high school and eats breakfast got counted in that group and that group. Does that make sense? Let me say that one more time because that's the hard part of this. So there's 36 students who are in high school. There's 52 students who eat breakfast. The group of students who are in high school and eat breakfast are counted in this 36 and in that 52, which means they all got counted 2 times. We can't count the same student twice. It's the same student. And so since that group was counted twice, we're going to subtract that off. And so these 12 people who are in high school and eat breakfast got counted twice. So I'm going to subtract off that 12 students. This is really just the formula we had on the other side. The probability of A plus the probability of B minus the probability of A and B. Putting it not in terms of A and B, putting it in terms of this problem. Probability of being in high school plus probability of eating breakfast minus the probability of being in high school and eating breakfast gives us our answer for the or. This is the overlap that we were talking about. So or means add the probabilities, but it means add the probabilities and subtract any overlap, any that are counted twice because they're in both groups at the same time. All right, so if I do this, I've got 36 plus another 52 and then minus 12. All right, so that's basically just 36 plus 40, and so that's 76 out of 90. And again, since 76 over 90, we could work on simplifying that. I'm going to get it as a decimal instead, and so this is, actually it's exactly equal to, this is 0.84 repeating, or in other words, about 84.4 repeating percent. So remember the or means add the probabilities, but if there is an overlap, we have to add the probabilities and subtract that overlap. All right, so that'll wrap it up with what we want to do with basically overlapping and disjoint events and how to read and interpret two-way tables. Tomorrow what we're going to start to talk about is conditional probability. So instead of looking at everybody, we'll look at just a certain group in one of these things and see if we can figure out what happens given a certain condition.